So, hello everyone. I guess only three of us are here. So, how are you guys doing? Am I audible?
Yes, ma'am. All well.
All well. Okay. So, are you Sri Naresh and Yash? Did you visited the week 5 lectures? I guess only 4 videos are
Yes,
there.
ma'am.
You went through them. Okay. You have any specific doubts, or we'll just go through the basic way that we go?
Let's just go through the basic way only, ma'am. It will clarify the doubts ultimately.
Yeah, that also works. I'll be speaking a little bit lightly because I have a sore throat. So let me know whenever it's not audible. So I'll try to speak closer towards the microphone. So in this week we had these two topics. First was the homomorphic processing. Later the second was for the waveform analysis. So let me know that if you guys are bored till now. Just because I felt that the course is going on and going on. But I guess from what started from this week is actually interesting. But yeah, filtering is something that we can actually implement it practically. If you guys know a few of coding and all, you can just write in some code, see some basic low pass, high pass filters, set some frequencies, take the Fourier transform. I guess you might have done that in your colleges, but just what do you say? Exposure of it helps. Like you can see that how the frequency is being cutted off, or if you want, we can take a session on that for a day and do it live, that if I'm doing over here you guys are doing there, and you can just see that okay how the signal is being formed, if we can do the thresholding based techniques and all those. So if not, then let's begin for today's class. But before that I'd like to ask that do you guys are able to see all the videos? It's like till week 12, or is it still uploading for you is like week by week?
It's been uploading week by week.
So till week 12 you're not able to see the videos there on the main platform, is it?
No, ma'am.
Okay, okay. Because what happened with me today is like perhaps opened the last year's session links, and then I saw that okay, if it's still week 12, then how am I able to see that? It's like then you guys can proceed it faster. So if some of you have completed the whole of the session, say till week 6, whatever it's being uploaded there for this year's program, you can just Google it, on not Google it, it's like find it on YouTube, and there is all links for the all sessions. So instead of waiting for a particular week, is if you want to, not at all necessary, then you can just go through lectures again and again, and there are all the videos uploaded there. It's also is like in a shorter window. So now this sessions that were being uploaded by NPTEL online, all are approximately I guess 30 minutes, 45 minutes, some of 1 hour 20 minutes ish. But there you will find some sessions like YouTube videos of 15-20 minutes also. So it would be nicer for you, you can also complete it fastly. Again, one more thing that I explored today was there's this course forum where you can I guess some of you are active there, so you can post your doubts there, and the other TS apart from me, they'll help you answer your question there. If there are more questions, you can just write in there that you want it solved in the live session. So that was one thing. The other thing was that probably tomorrow's 28th, yeah, there will be a live session by Professor Sudipta. So I don't know that what's your course in your classes being taught on, or it's like I know that two of you, probably Ayush and Yash or Srinaresh, someone. So you have this in your like college being as compulsory. So if chapter 8 and chapter 9, that's analysis of non-stationary signals, and the other one was probably based on some segmentation methods and all, if that is also in your syllabus, you might want to attend those two sessions. So he'll explain it in the live session, so you might even get a chance to ask about the other doubts that you have as well, because mostly as he says that the sessions are not full, so you can also dig up into the previous doubts if you have. So that's it. Those were all the updates, I guess. So we'll start for this week. So what we have for this week is this homomorphic processing. I like this because You'll find this everywhere, that is in signals, in image processing, everywhere. So what it does basically is that you take a signal, you take its Fourier transform, just a basic analogy I'm telling you, and then we'll go towards the deep also. It's like in a brief understanding. So you take a signal, take its frequency, like convert it into the frequency domain, then compress the signal, because you don't want the dynamic range to be distorted, but you also want to conserve all the frequency ranges, reserve them all. Then do your analysis, and then again expand the signal back and then store it. It's like take the inverse Fourier transform if you want to store it in time domain, and that's it, your processing is done. So this type of processing is mostly for linear based filtering. More of the approaches which are based on linear filtering, say all your high pass, low pass filters. But there are also some approaches which are non-linear approaches. If I have to say, last time it's like studied about the match filter. So there's also one kind of filter called as chirp filtering. So this chirp is similar to how birds chirp. It's like the sound of bird chirping. So what this filter does is like it will match the maximum amount of signal frequency, or it's more of similar to the correlation, how we do the. So what it is actually is like wherever you find the energy is maximum in between the two segments at a particular instant of time, it will give you the maximum energy, and you'll be able to localize your target whatever you want, or remove any unwanted noises or sources. So that way we have some of the non-linear approaches. But what people are trying to do is like instead of digging up into the non-linear approaches, because what non-linear basically is that what doesn't work in linear techniques or this pipeline will normally follow the non-linear ones. So what we do there is we just take the signal, perform some basic methodologies, or first do the linear one, then do something else that comes out of random, and then that's what you called it as non-linear. But there are also fundamental regimes defined for the non-linear processing. But what actually are people trying to do is like linear filtering, the method, how you approach them, it's quite easy, computational power is also less. So people think that linear methods could be explored more and more, and you can get more insights from them. So this analogy was given by sir in the live session, sorry, in the recorded lectures as well. So the thing behind this is like if you take a picture and you're standing, say you have this nowadays people do TikTok and all, so they have this light in front of them. I don't know what that light is called, it's like, but just a standee with a bright light, the
Ring light.
circular. How, what?
Ring light.
Whatsoever. So then that makes it look, it's like the complexion is nicer in that way, so it looks nice. But the more and more you go away from it, the more and more less light is there in front of you. So similarly now I'm using two sources in order to project, so that one gives me good energy, whereas other is like for casting. So in the same way, so what happens here is like distance is playing a role in here. So as in how you go away from the source that's illuminating something, the reflectance and the energy of the reflectance, it also gets lesser and lesser. So this is something that we see is that now in here, normally what we saw is that we have a signal, and we always say that a noise is additive noise. But here what happens, if you go away from the distance, it's like in a multiple of 2, in a multiple of 4, whatsoever it would be directly or linearly proportional to it, or it will be quadratic or will follow a polynomial or so. So that indicates that something is not added over there, but it's multiplying and giving over power of something or so. So that type of noise we refer to as multiplicative noise. And that's in a way very sometimes it easier to separate it out in between two particular segments, but other times it becomes more difficult. So that's why here we are choosing the approach of homomorphic filtering. What it does is like we take the signal, take the logarithmic, compress it. Now you all know that log a of a times b is a plus b, so that way we can actually differentiate it out. But what it does is like in a way you are compressing everything out, so noise is also being compressed, so your dynamic range is also being compressed. So in a way you don't always want that to happen. So there are some pros to it all as well as some cons to it. So in a way, if you can see over here that if you have a system, say which is illuminating something, these are the coupled receptors which are taking in the signal. So at each and every stage it's being added. So this is just a normal analogy to show it to you. So it's getting added, but there are some other pipelines also which give you a feedback and then getting changed, right? So here it's a non-linear medium, but what if you're directly standing and throwing it to some light? So that's multiplicating and then going it back. So just a simple analogy for showing the same. So what happens in this homomorphic filtering is like this: like you have a signal or source, you compress it. Taking a logarithmic is nothing but compressing the dynamic range of the signal that is in between the maximum and minimum amplitudes of it. So say if I have a signal which is being say which images do I say? Say some intensity or color intensity images. Now I want to show them in grayscale. So what I'll do for those grayscale is like first I'll obviously change the color bar of it in order to show it in grayscale. But now see that the system's dynamic range through which I was taking the output was in between 60 and 0, negative 60 and 0. So in order to represent the image, I need to give the c-axis in a way that it's presentable in between 0 and negative 60. So there and there only my output or image would be shown up, or else it won't. So we compress the image. Then after compressing the image, we get this low, it's like we pass it through the low pass filter or the high pass filter, depending upon the application which you want to do. And then what we saw is like basically we are multiplying everything and then adding. So low pass filter is essentially taking a cutoff lesser than a particular cutoff frequency. Here it's lesser than one, here it's greater than one for high pass filter, adding them both, and then finally taking the exponential in order to reverse the process of what we did in logarithm. So these systems are very important for linear invariant systems. They are very important for the ease of analysis, very powerful mathematical representation of the signal and processing tool. But what it follows, if you seeing over here, we aren't actually eliminating one source and taking the other source, or eliminating the other source and taking the one source. We are actually using the principle of superposition. So it binds to the principle of superposition, whether it's associative, commutative, all the properties it follows. So it's in a way it's called as generalized linear filtering, because we are not only using the basic filters which are low pass and high pass filter, which are just the steps to go towards a band pass or a band stop notch, all those filters. So this is in a way called as generalized linear filtering. But again, you need to have some form of mapping or linear transform, so that it's called as homomorphic systems. So what this mapping or linear transform was that, now if you're compressing a system and then taking the exponential of it, now you need to know that what particular intensity value was matching to that particular pixel when you're taking the exponential form of it. It shouldn't be that, okay, I compressed the image of an apple and then I exponentially wanted to take the inverse log of it, and then did the exponential of it, and then I got a picture of banana or orange, something like that. So you need to actually know some intensity relationship in between the two. There should be some mapping or a linear transform playing into their role, hence that's a linear filtering, hence it's called as homomorphic system. So as you said, it follows the principle of superposition. So first was the associative property, that is nothing but if you apply transformation on a system that's adding two inputs, you can also get the same output when you are adding the transformation of each and individual inputs to each other. Similar for the scaling one, if you scale the signal and then take the transform of it, it's similar to taking the transform of the signal and then scaling it. So everything's just the same, the transform and scale or scale and transform. So this is just the cornerstone of the linear systems. What follows through it is the more and more steps which stands on these steps. So the generalized system. So if you all, if you might recall what happened in wait, frequency and time domain. So when you had a Fourier transform of two signals in time space, when they were multiplied in frequency space, they were convolved. Essentially, the inverse, that when time domain, where they were convolved in frequency domain, they were multiplied. So here the generalized principle is that if you multiply the signals in time domain or a particular domain, it adds in the other domain. But here the domain is not changing, but just in a way how you represent or suppress in bit, it's like differentiate the two signals, it changes. Now here you might see that, okay, this is multiplication, this is addition. It's actually the inverse of it. This stands for adding the two signals, this stands for multiplying the two signals, because essentially we are multiplying everything. The transforms are getting multiplied. Now same follows for this one. So it was this terminology for new for me, that C wait a second now. Okay, sorry for the interrupt. Um, Here. Yes. So now this terminology was something that if you, it's like it maps the scalar quantity to a vector quantity. So what happened is essentially is that this x of x1 of n, that's whether it's a discrete signal or a continuous signal, when we map a scalar to it, we represent it as c colon x1 of n. So in a way that it's also represented as additive. So this symbol is represented for additive. So we'll see in the later slides. So here, such systems are said to obey the generalized principle of superposition. Input operation this, that's a rule that combines to each other, that adds them. And this colon, that a rule to combine the scalars that we saw to an output system with the operation of this plus sign and this dot sign. So linear systems are special cases where this and this are addition and this are multiplication here. So there's some slight changes in the terminology, but it's not always the same. We don't always use this signs. It's always like plus multiplication, the normal ones. So don't get confused in between this. It's just for the starting one. So it's same way that when you give an input to a signal, that's multiplicative but also additive at the same time. When you get it out, it's always separated because you want to separate two sources. So just bear in mind that okay, if your input is going along with some noise, in the end you want to separate the input or the signal of interest from the noise. That's it. So here are the properties that if you have two signals converge with each other, you can actually reverse the role of them. But then you might also notice in real life the operations aren't the same. That okay, if I take the notes first and then I take the notes after the class, so it's not always the same. Similarly, for two signals which are being added, if you change the order of them, it would be the same. The results are same. Associative, that's an order used to combine items. So if you change the order in which the items are combined, the results won't change. It's always the same. So if x of 1 of n is convolved or say multiplied or added with this x2 and x3 of n, if you change the order and take x1 and x2 at first and then x3 at last, it's always the same. So these properties are something that we all are studying from our fundamental classes. So it's always the same, and these properties follow or bind the core roots of a particular linear system. So at last, the multiplicative homomorphic system. So first what we do is like separate. The essential goal is to separate the components out. So first we take the logarithmic of it, then add the systems, then take the exponential of it, and then compress it up. So take the separate components that we have in there. So taking log is just so that we can separate the components at the end and we can perform some linear operations on them. So if you have some systems where okay, if it's something something like x raised to something and exponential raised to something, it's and both of them are multiplied, it's very easy if you take log and to separate them and again take log and then separate them in the end. So you'll be able and then represent all of them by some say different constants or variables and then take the exponential of it. So in a way you weren't actually able to perform some nonlinear operations and that you actually don't know what the basic physics is behind them, but you are able to perform the linear operations bearing in mind that okay, this signal was the previous signal. So it's always almost similar to how we do in integration, that if we don't know a particular sign or symbol, then we take a variable for the same and then we differentiate it, integrate it. In the end we always place them in and follow the limits for the variable that we substituted for. So similarly, so okay, here. So first, if you take an input signal as x of n, that stands for x1 of n and times x2 of n, you take a log of it. So log will essentially differentiate both of them. That is of ab, that's a plus b. Now here what happens is the second. So x of n was actually, now here they represented x of n as, now we know that okay, a particular signal say e raised to j theta, following the Euler's rule that we have is cos theta plus j sine theta. So a particular signal that's always represented in a way that it's a magnitude times the phase. So what happens if we take the log of the particular the signal, it will separate. Now we are separating the components out, so it would be log of the magnitude times j, that's the imaginary part of its own phase. Now here the phase is in a way that it can always be from negative pi to pi or 0 to pi, and this phase inbuilt it introduces the discontinuity in the signal. How? Because now you're taking a log of the signal. Now you might have noticed that whenever you take logarithmics or exponentials, the signals aren't always continuous. There's a discontinuity that occurs around the origin as well as whenever the signal peaks and then crosses the zero line. So this discontinuity happens. But then whenever you take the exponential back, The range you'll always find is between 0 to pi. It's not within negative pi to pi, it's always causal. So this is something, okay, it is like that, so I can't actually have the basic reason behind it, so it's like that. Then you take the complex exponential of the original signal that you have, exponential of the log of x of n. You separate the components out, eventually get the signal that you had x of n. So this is just the basic process that's behind the homomorphic filtering. Again, so if you have an input
Ma'am,
signal like this, yeah, yes,
ma'am, I have a doubt.
yes, go on.
I'm in the previous slide. Yes, ma'am. So, ma'am, in this, no, ma'am, the next one.
Yeah.
Ma'am, so in the complex exponential, ma'am,
Mm.
what is the use of expanding first x of n in the log e to the power log x of n? Because it can be directly written from the base change property. If base is e of log, then we can directly write x of n. This doubt I was also having while watching the video.
Yeah, so here we are taking natural, not the natural log, we are taking log base 10. So if you're taking natural log, it's always fine. But then if you take natural log, you need to also invert it in the same manner. So you're getting my point? So it's always, so how do I say, okay, it's always easier to implement systems on the base 10 or say base 2, but not on the base of 2.7, because that's a decimal fraction that adds in there. And due to this decimal fraction, the discontinuities in the signal while compressing the signal or expanding the signals, it increases. So that's why what we prefer mostly is like taking log base 10, because you know the values for the same, while taking log base to e won't always give you the exact values. So this is just to represent that, okay, now instead of taking this exponential j raised to argument of that particular signal, that's the phase of the signal, one might directly write the angle that's associated with it. So it would be just the log of that angle, so it won't be e raised to something. So it's not always the same like that. This is just an ideal case. That is that explanation fine?
Yes, ma'am. Ma'am, it means that the log is having base 10, not e.
For now it isn't, but then when you see that if you take this exponential log, you see this base would be similar, hence we eliminated it, hence it was the magnitude same. So here they took it as base e. This is something that, okay, sir said he'll resolve it in the live session, but initially when we take it's log base 10, because eventually if it was log base e, this won't be separated it out. So it's fine.
Yes, ma'am.
He'll address it. So yeah, so if the input signal is like x of n is equals to x1 of n times x of 2, so if you take the log of it, it's like separate the two signals out and then you represent it by some other variable, say x cap 1 of n and x cap 2 of n. So then you can use linear filters in order to separate the component signals out of them, and then again take the exponential of the signal to reverse it back to x of n, that was x of 1 of n and x2 of n. So these multiplicative homomorphic systems are basically how we saw the camera example. It's like the illumination component increases linearly, but the reflecting component depends on the distance. Distance eventually, if you take in the frequency domain, would be the frequency how you're increasing. Now it would be constant, but after a particular point it saturates. So it's just that multiplying, but okay, after a certain point it's not giving you anything. The all the outputs have been saturated, so it will be flat enough there. So as we saw that, okay, the slide didn't change. That x of n is like in time domain, if you're convolving, frequency domain will have the multiplication of both of them. Now you take a complex log. Now how you represent the log also depends. Now here they have actually written that, okay, you're taking in complex log in a way that it's like, okay, it's base e, but then here you can't actually differentiate the signal, and you need to have an phase property to it, because it also gives you some important information. Phase always exploits more features of the system with respect to the magnitude of the system itself. So same way, the magnitude and the exponential, this phase of the component, then you take the exponential log and the signal is there. So this is in a way that you're doing homomorphic deconvolution. That's just the same way that how we did homomorphic convolution or homomorphic filtering. So the process is always the same. The terms in a way that how you differentiate it or how you write it, it varies, but the max is always the same. So all process here, that first you take the Fourier transform, then you apply the logarithm. You want to take an inverse Fourier transform, it also works. Then you have the signal in time domain itself. So in a way it's nice, because but then there are some signal based processing methods that is like in time domain you can't actually get that resolution well that you get in frequency domain. So in frequency domain, the things are also faster to process with respect to time domain. In time domain, you're limited by the sampling frequency also. But in frequency domain, you can manipulate that frequency, have more number of samples, include more number of samples, interpolate the signal, extrapolate it. So there the processing becomes more faster, as well as you get more insights about the signal or the system that you're playing. But here, okay, they are doing it in time domain, so do they. So then they apply a linear filter, take the Fourier transform of it, apply exponential, and then take again the inverse Fourier transform, retrieve the signal back again. So the whole process of homomorphic filtering processing, it follows like this. So there is an example of vocal tract response here, case study, which says that if you have a speech signal, so when we utter the vowels like A, E, I, O, U, the signal comes from glottis, something there is near the pharynx and larynx. So it's being measured through this glottal pulse. So that's a repeated sound wave that happens. So if you touch near your larynx or here where you can, if you all are males here, near your Adam's apple, whenever you speak, you feel a vibration that's going through in. So that vibration is actually convolved with the transfer function of your own vocal tract. It's like how long your esophagus is, or how long your larynx tract is, how the number of rings are, or the width of those rings in between them. It will be convolved with it, and accordingly the voice changes whenever you have, say, a sore throat, or whenever you're singing something and you feel that okay, that voice isn't yours, but you're trying to mimic someone else's voice. So everything changes. So in a way it's convolved with the thickness in how you're trying to say, how your lip sync is, all this. So you might wonder that it's a sequential process, but it's not actually that uniform or linear. There can be changes. It can be modulated in a way that whenever we are trying to we are hearing a new singer's voice, but we suddenly try to mimic it whenever we sing it along with them, so it gets modulated again and again. So human bodies like that. So it's nothing but continuity, and again it changes in frequency, sorry, the phase changes with respect to the frequency. So there will be a term next to this that's called as phase unwrapping. So what that essentially means, I'll just show here this phase unwrapping. We so it's like we haven't explored more, but what it is actually is that whenever you take the frequency domain of Fourier transform of a signal, whenever you're working with phases, it's always necessary to incorporate the multiples of 2 pi, or say multiples of pi, in a way that you don't actually miss out on something and your signal doesn't have a discontinuity in there. So it's normally a critical step to ensure that you have all the appropriate multiples of 2 pi, because whenever an odd multiple comes in, now it would be difficult for you to process for that component, and you'll have to separate it out, and then it's like singularly process it. So it's always nice to have all the multiples 2 pi. So this is what they refer to as phase unwrapping. Okay, so this is like the glottal wave that we have. We take the Fourier, it's like we pass it to the impulse response, you get the voice speech. So we get again Fourier transform of it, you take the log represented by some other functions, take the inverse Fourier transform. Now the signals have been represented, it's like they are represented as a additive, as like in a linear operation. So this frequency somehow they called it as Q frequency. So okay, and this term that we get after the inverse Fourier transform, it's being referred as complex cepstrum. So if the original signal is real, then this part what you get is also real, the cepstrum part. So that's it. That, and again the phase unwrapping was important here so that you don't miss out on any particular frequency responses. So in a way which by like through which we actually use this frequency responses or frequency domain processing, is that you always exploit the phase of the signal and you don't want to miss out on each and every frequency. So that's why you always want to have every multiple point that you can actually get. So it's always good if you have the entire unit circle with you. So take the entire multiples of 2 pi, or just a single circle of like from 0 to 2 pi. That's it. So what happened here was you had a sound sample, then again you windowed it. This comes from our previous sessions where you had a non-stationary signal. You separated it out into different stationary segments so that you can process it. So those segments weren't actually stationary, but you can see them as quasi-stationary signals. Then you take the frequency domain, convert it into frequency domain, take the log, inverse it. So that is something, this type of processing over here, they refer to as cepstral lifting. Now, this process of lifting, when applied to voice and speech signals, it's called as, it's like the filtering is called as lifting here. So just a random word for it. I just reverse the word for filtering. So here the transfer function was a low frequency, but the excitation that we give is in high frequency. Why the transfer function was a low frequency, can you guess? And why the excitation is in high frequency? Okay, only we three are there, so you can just jump in or turn your mics on and say. So excitation is in high frequency. What is excitation here? The sound sample is an excitation. So whenever you try to speak something, it's not always in low pitch, but with respect to the system that you are doing, with respect to the system's own rest state, it's in high frequency. And the transfer function, that's an impulse response, is being traveling there up from down. So it's not actually that high in magnitude or having that major high frequency components with respect to what you actually gave it in the first. So it's a lower frequency one. That's it. So then we'll look up into the waveform analysis. So that was all for homomorphic processing. If you have any doubts, let me know. But homomorphic filtering is just all about that. For the exponential log base 10, if you ever feel the need that, okay, this type of log will feel better and I can process my systems better in this, it's like compressing it in this way, it's always fine. Just to mention it, okay, I'm doing it in this way and this is how I'll be processing, but don't change the base of log in the later processes. Be it the same for the entire process. But then you have to see that which particular methods will work for which particular base. So there are some which changes, most doesn't change, but some do change that I know. Okay, so you have any doubts for homomorphic processing? If not, we'll go into waveform analysis. That's only few slides and then the assignments.
Ma'am,
Yeah.
ma'am, is it important in homomorphic filtering to separate a convoluted signal? The exponential transform which we are taking of a signal is of must be of time domain or frequency domain.
I didn't get you. Can you please repeat?
Uh, Ma'am, I am asking that in homomorphic signaling, the input signal is convoluted. So, is it
Mhm.
important that the signal should be in a time domain, or it must, or it can be in frequency domain?
Yeah. So see, mhm. So basically, whenever you try to record a signal, it's always in time domain, right? When you process it, you convert into frequency domain. So whenever you are trying to acquire something, it would be always varying with time. So say an oscilloscope where you take readings from your own setup, how the signal is being varying, or how the power supply is giving you an output, it will always with respect to time. If you have an option to get in frequency domain analysis, it's like waveform that's in frequency domain, it's always nice. So you can directly go on and process with it. It's not necessary that they are convolved. It is convolved or multiplied because you always have some other components along with it. Say noise is there, or some other components are like there. So in a way, here it's noise that we are considering. For an ideal case, it would be just noise. For other cases, that would be also some components. So say if you are having, you might have heard of the example that's called as cocktail party problem. So what happens in there, if you give a mic to a particular group of persons, you won't actually figure it out that which person is trying to speak. But if you, it's like, everyone are equidistant from you and say I'm standing in the center of the circle and r is the radius from which everyone are standing. So I'll be able to clarify that which particular person is saying, and there would be just a single source that's giving me an output, not multiple sources are involved with it. But that's not the case always. So you always have more than more secondary or sub sources involved in the process. So you actually, the signal is multiplicative or convolved in it. It's like it's inherently it is like that. So if it's not convolved, there's no need to do this homomorphic filtering. but it is normally like that, hence we do this. You get it?
Okay, ma'am.
So we come back for a waveform analysis for the basic how the biomedical signal processing is being done. So this we saw, I guess, multiple times within this week 4. It's like till week 4. So we have a patient and then we acquire the biomedical signals from them. What sort of biomedical signals can be ECG, EG, EMG, EOG, gastric, galvanic skin resistance, and all of those like that. So the signals which are then converted by the transducers into electrical energy, that's biopotential, is being converted over here. You isolate it in order to remove the noise, but it's bear in mind that it's not something that you're trying to do over here is a process of artifact removal or so during the signal acquisition. Then you amplify it, do some filtering. Now there's a time to convert the signal back to digital form. So you convert it into digital, then you remove the artifacts, do the signal processing that you want to do, then extract out the components that you have, and finally it's given to the physician so that he can diagnose, and later the treatment would be followed up. So this is how biomedical signal processing works. So in it, we are trying to see that different case studies over here, that how different waveform change with respect to the abnormality that's been followed. So here is just a basic ECG. We all saw that okay, there are two types of technique through which ECG conducts. One was the systemic circulation, other was the generic circulation. This pulmonary circulation. So again, in between them also we saw the electrical conduction of the heart. Now there is this P wave, so there's this SE node, that's a natural pacemaker of the heart which initiates the signal, and then it goes to the AV nodes, then the bundle of his, the Purkinje fibers, everything contracts, and then we have the ECG waveform. This all follows and completes in between 0.8 seconds. That's a cardiac output of our entire, through which the blood pumps, and then through the aorta it goes into the systemic circulation. So again, that P wave here represents the atrial depolarization. Then you have the QRS. This is the PR interval. Again, the delay in between the SA and the AV node. This for the ventricular repolarization. Then you have a flat segment that we also use normally in our own signal processing as an isoelectric segment. So that through which, if there are some noises, you take that particular segment as a reference and reconstruct your entire waveform with respect to this segment. Then you have the T wave that represents the ventricular repolarization. So just imagine that you have an abnormality within the it's like this waveform, everything will change. And if you have an abnormality, that means that some things are not working properly, that there is a regurgitation, backflow, or some valves are not closing properly, or our septums are not closing, or there's no complete fulfilling of them. Something is repolarizing at the time when some other is being not being repolarized, or it's not having an entire particular time period. So the waveform alters. So we also saw that there were different kinds of abnormalities associated with it. The basic ones are like bradycardia, tachycardia. It's like slower heart rate, higher heart rate. Something inverts, the P wave will invert, the T wave will invert, the complex would get shorter, the amplitude would be shorter. So there are different types of them. So if at all, if this is being asked, you can refer to the slides also in the book, but I don't think so it would be in that deep. But you can just have a look at which particular abnormality is associated with what kind of changes in the ECG spectra. Here we only have a few of them. So there's something called as bundle branch block, that's represented by BBB. But something that's more important than this BBB is this blood brain barrier. But don't always get confused in between bundle branch block and blood brain barrier. So what happens in here is that one of the ventricle gets a signal first, is that you can actually get two R waves here. So if you might recall that last time we saw the segmentation techniques and we saw the thresholding based techniques, where we were actually getting the peak of the signal. Now, how do you find the peaks of these two signals, and how do you differentiate is that, okay, I have these two peaks. How do I set the threshold in a way that one peak is almost similar to the P wave and another peak is more higher, or the maximum peak? So something that follows the P wave is something that's regularly, or the process is going on very smoothly. Something that follows next to it is something that's abnormal. It's like a maximum amplitude peak and then followed by your T wave. So again, you might have noticed that T wave is in the inverted amplitude over here. So here what happens is like something that's regular is with respect to the P wave that's being continued, and then something that is delayed to it is the abnormal one. So just a basic question, that where will you notice these changes, in which kind of leads? So we had bipolar leads, we have unipolar leads, and then we have precordial leads, that's what chest electrodes. So in which specific leads you will observe these changes? be it in bipolar or unipolar or precordial chest leads. I guess it's there in the website. Sorry, in the slide. Can you just speak up? No. Okay, so this we observe in more of this precordial leads. So those are actually in a way placed that V1 to V6. Those are placed that, okay, if I have some, those are actually based on the four chambers of the heart along with the ground and a bone associated with them. So in a way that you get an information at this particular lead and the other leads. So I have few examples of here. Say if it's a V1 and if it's a V6, if it's normal, you see a normal wave, but okay, there can be changes associated. So all of them are bundle branches, bundle blocks, but sorry, bundle branch block. But again, there you'll see the changes that, okay, the R wave is heightened, so the amplitude of R wave is higher. Now, if it's a righter one, then you'll get the signal delayed in the right one. But if it's a precordial 6, now here what you need to know is that which particular lead is associated with what location. It can be medial, it can be sternum. The locations will change. With respect to the locations, you'll be able to differentiate that, okay, this kind of block is associated with the right ventricle, or this kind of block is associated with the left ventricle. So for the left one, you might have seen that, okay, this is actually entirely flipped, and this is something that you get this two always, but if you do maximum peaks, you'll get two peaks out of here. But if you set the threshold in a way that, okay, it's like this, you'll just get a single peak. So you won't be able to differentiate that, okay, how. But then again, you can see that the complex has been widened out. So this much time you don't require a signal or the ventricles in order to depolarize. It happens very quickly. So from there also you'll be able to see that, okay, there's an abnormality going on. So then there's something else called as ischemia and infarction. That's in a case normally a slang or like a technical term for heart attack. So what happens is like blood supply is not getting there, and all the muscles, the nerves are just following along with respect to what they had. Oxygen is not getting purified. So in that way, the segments would be heightened up. So there's a relationship between action potential and the STT segment. So what happens there is like it widens out. First, normally we saw that, okay, it was depolarized. Then after depolarization, our waveform was quite smoother like this. Initially, if you remember that action potential curve. But here what happens is like we have a plateau phase and then it repolarizes back. See, normal essentially our initial ECG curve. But then when there's this ischemia, you get this widened out, or this ST segment, the elevation increases, the difference in between them essentially increases. There's actually a dip in between the ST segment. So through this variations, you it's like physicians are able to make a diagnosis that, okay, or because everything is working into milliseconds or microseconds, so you're able to see what exact changes are there. So each and every point is important. Then if the ST segment is elevated, see, if the baseline for it changes, then also there is a change. If the baseline is actually going down, if it's depressed, then the changes are associated with it. So the ECG waveform, it changes with respect to an injury, ischemia, acute infarction, or an old infarction. So the changes or infarction are different types, and it might change with this. So different manifestations are there based on the EKG or ECG. So in for case of injury, you also see that elevated one inside. So this is something that, okay, when someone has something called as angina, that's you don't know what's the exact cause of the chest pain. So there what happens, like basically we see that the ST segments are elevated within a few minutes, but people don't take, it's like not people, but physicians don't take it that seriously, because they know that, okay, if the following ECG is following along and it's normal and no such changes are there, then it's actually due to the injury that was there. So if someone's playing cricket or so and got a ball directly on the heart, it's like not once but see a multiple times, then it is something that, okay, now you are trying to provoke it, and then the onset starts. Then you have ischemia where the waveform directly inverts back. Then you have acute infarction when here the difference in between the P wave and the dip it takes actually shouldn't be that higher, but it increases, and hence the infarction is said to be acute. Then if it's an older one, then the width or depth how which it should be coming, it's normally stable, or by default the complex segments for them or the time segments for them are given by default. So then what people do is they note the ST segment length. This ST segment length, if it's normal, and then if I'm seeing a higher dip in here, then they say, okay, that's an older infarction. And from there only, physicians are able to, it's like back calculate that, okay, if this is a first heart attack or a second heart attack, it's like how many heart attacks happen through this way. So like that. Then another is called as ectopic beat. So what this ectopic heartbeat is like, if you have a missed heartbeat or you skipped a heartbeat. Now we all have hiccups. So what happens in hiccups is like, you, I don't know what's the basic cause for this hiccups, but some say that, okay, if you cough a few more times, or if a person is scared, it's like scared in a way that he forgets and he's distracted away, this hiccups will stop. But what happens in this hiccups is also that you miss your heartbeat. You missed an entire cycle of through which the blood supply is supposed to be purified and then going out to your entire body. And so also, if you might have noticed, I do notice sometimes, but do notice the other time that you get an hiccup is that you might notice numbness near your elbow or the parts near your leg. So this is why the areas where blood supply take more time to travel, because it's actually into the periphery as well as distal to our heart. In so to reach them, to supply the blood over there, it's actually more it's like it needs to travel more path. So when people say that if you get an hiccup, try to cough near your elbow or try to jump, it's just because the parts that were numb, now you'll be it's like giving more number of blood supply to it by doing these activities. Since the blood supply increases, the heart rate is normal and the hiccups stop. So it's something like that. So then we do analysis of this ECG wave. So then it's like we saw that how different types of abnormalities were there, and we were able to notice, not us but the physicians. But now if something is there that we want to notice, if my thesis is on ECG wave, so there are some kinds of analysis that we can do and we can separate them out. So initially we saw that there were thresholding based methods, peak detection based methods in the last lectures or last week's slides. Now there are some other ways also. The first one that was proposed by this Jenkins et al., it was based on this correlation coefficient. So will someone just say that when's the correlation coefficient, not what's written on the slide, but that when's the correlation coefficient higher and when it's lesser? Just take a basic example of autocorrelation or cross correlation. Okay. Oh, you spoke up. Are you spoke up? Shri Naresh, will you give it a try? Are you there? Okay, Yash, go on. How come everyone's not here? Oh, okay.
Ma'am, I know the answer.
Yeah, please go ahead.
Ma'am, correlation is normally high when two signal matches each other. That means their maximum value is one. So at that time.
Yeah, same. So normally what we do is like we take the regular ECG heartbeat to be our own template for in order to compute the correlation coefficient. So what people say is that if you have a normal template, a normal beat, so just a PQRS waveform. Now you might ask that what's a template now here? So template is essentially your own beat, which was taken when you were doing some activity, say for treadmill based activities and all, through which people assess the heart health of the heart. So from there, wait. hmm, hmm. So from there, we are able to map our own heart rates to what it was previously. So if it's normal and there were no changes and the heart is functioning healthily, the correlation coefficient is greater than zero point 0.9. So it's very high, but it's lesser for the abnormal cycle in a way that the energy, essentially what I said, that the energy won't be matched up. But again, the normal heartbeat would be higher. It would be higher with respect to the abnormal ones in some cases, but when the QRS complex matches, it might be higher. So this is something that it is very highly affected or sensitive to noise as well as some other corruption in the signal, basically like this. So from here you can't actually differentiate that what was the basic abnormality, but it's an easier approach to do when you actually have the signal segmented out very nicely. So you can see it and process it into the window that you want to do, and then it's done, your processing is done. But correlation based coefficient method, this doesn't normally works in real time. No, in real time people normally nowadays use auto regression and all those kind of techniques. So we'll see those techniques in like later sessions of this course. So it's like that. So this kind of didn't work out that much, but this was the first proposed by Jenkins et al. So then there came in another method called as minimum phase correspondent and signal length. So essentially, what is a minimum phase over here? That's a minimum phase of your own signal. So why the minimum phase? It's like you have, okay, we'll probably say it in further slides, but okay, you all know what Z transform is. When we take a Z transform, you have poles and zeros. Essentially, people say that the system should, in order to be stable, it should be towards the left hand side of the system, as well as it should be within the unit circle. It should incorporate the unit circle. If it's not, it's an unstable signal. If it's a causal signal, it should be towards the right hand side. If it's an anti-causal signal, if it should be the left hand side. If it's a non-causal signal, it should be both sides. Sides in a way that of the geometric plane is like 0 to infinity, 0 to negative infinity to infinity, like that. So our ECG signal energy is concentrated in 80 milliseconds. So that's actually of the QRS complex, because there only you'll get the maximum energy. So is it obvious? And if it's obvious, then how it's obvious? I actually said, but okay, it's okay. You can repeat it. So essentially, because QRS has a maximum amplitude, and just because it has the maximum amplitude and it happens very quickly, the ventricular depolarization, it's situated, it's like within the 80 milliseconds window slot. So that's very less with respect to the other waves which are more wide. So last time I guess we saw which segment was higher and which had more number of time seconds, 120 milliseconds or so was the maximum there. So this signal energy is concentrated within the QRS complex, just so because ventricular depolarization is very fast, there are no delays within that. Bundle of branches, bundle of his work very efficiently. So that is why we have the maximum energy there. And then I guess you should mute up, it's like unmute yourselves and hear only. So this P wave and T waves, relatively we have a higher amplitude or lower amplitude, very quickly.
Lower.
Yeah, yes. So then what happens is that after the T wave, the activity diminishes, and later a period, a brief period, the P wave emerges. Can you say that what is this later after a period is being referred to as? There's a name for that period which we saw in action potential. That when you give the response to the system, it won't react, and after that particular period only, the system would react, and hence the process will complete. And here in heart, it completes within 0.8 second. That's a cardiac output. So what is this period called as? Someone? So, okay, it's essentially that refractory period. So, when you give a stimulus or any perturbation to the system, it won't react, and after a early complete time, when it comes to rest and everything's normal, the another wave will emerge and it will react to it, and then the process goes on. So any abnormalities will cause the QRS complex to widen it out, to shorten it out, and the ST segment to bear a non-zero value. Just because ST segment is the highest one, it won't be non-zero always because it's not there in the reference. Then the reference or the baseline will shift higher and upper like that. So we might say that the signal energy would be then spread over a longer duration. So the signal is now the ECG won't be within that zero point 0.8 seconds or so, or the cardiac output within the zero point 0.8 second. It would be spread up entirely. So now you'll be able to see it completely, and but you won't be able to differentiate the individual frequency components out from there. So how this technique goes on is, you have a signal say x of t, you estimate the density from it. Say energy estimation is nothing but square of the signal. Now everything what we are talking over here is positive time domain, positive window, causal window. That's follows from 0 to say the time period of the signal. That's a capital T. Now you compute the total energy, like integrated x square of t delta t. Now the centroidal time is nothing but the first moment of it. So you take it and then divide it by the average signal component. So with respect to each and every time segment, divided by the average part. And dispersion of energy, how the energy is being spreaded from one point to the another point in time. So with respect to the space, and then similarly multiplied with respect to the energy. So this is t. Now it's substituted by t minus tx. So that is how it is. So now this idea, now you might see that okay, it's in t, that's continuous domain. It also follows the same for the discrete domain. So if you take a summation along in here and you just replace this t by n, that's the number of discrete samples, whole inner just like the formulas and the theories behind it, it follows along. So that is where the linear operations are very easy to compute as well as to process them. So the term there, that was a minimum phase signal. So as in Z transform, we have a stable system within the unit circle, or which includes a unit circle, which has a unit circle within it. But if it's a non-minimum phase signal, so the signal has more spread. So in a way, it's spreaded over the entire duration, and you won't be actually able to differentiate the individual peaks from there. So from there only, this was all about the waveform analysis. There are some equations associated with this minimum phase signal, more of them, but the major ones were this, hence I incorporated this ones. The last later ones were something like, okay, you just need to know that how the process is, and that's it. So it doesn't has much physics associated with it. So you have any doubts associated with waveform analysis? If not, then we'll do the assignments. Will be done probably by 7:30 today then. Any doubts?
Ma'am,
Hmm.
ma'am, if the Z transform of a signal has zeros inside and outside the unit circle, so what that signal will be called?
So if it's inside and outside of the unit circle, so then you need to see that are you actually able to form a circle from the given points that you have. So basically what happens is that, say if I have one at positive 1, other is negative 1, sorry, positive 2 and negative 2, and then there are some poles on the axis. Through them I'm forming a circle, and if the circle is lying somewhere in between them, then I'm telling it that okay, it's like that. But for the system to be stable, we also say that the pole should be left inside of the plane that we are saying. So that is also in a way to see that okay, if it's stable or not. So
No,
if
ma'am.
some,
No, ma'am. Is it like is that signal is minimum phase signal or maximum phase signal or a composite signal? What type it is?
assignment question.
I'm asking like that.
So it's just that if a system is stable, that type of system you refer to as minimum phase signal.
Okay, within unit circle,
Yeah,
which is
within
within
unit
unit.
circle, or if it's something incorporating the unit circle, having the unit circle with it, that kind of systems.
Okay, okay, ma'am.
Okay, so assignments. You all, it's like just you, Raj, Naresh, and Yash. Please do unmute yourselves and speak up the answers. So we'll be done within it. Oops, what happened? Huh. Okay. So homomorphic filtering is used to separate. multiplication of two signals, subtraction of two signals, addition, or convolution. So probably some of the questions are like MSQs, multiple choice is like you can have multiple answers to it. Some are a single option kind of them. So you can have a look and tell me a appropriate option for the same.
D. Convolution of two signals.
Yeah, better read it again. First one is something like multiplication of two signals.
Hmm.
So that also follows.
That also
So the
follows.
answer, yeah, because now the signals are multiplied. If you take
Hmm.
directly convert into log domain, you'll be able to separate them out. If they are convert, you convert into frequency domain, then you do it. So there also it follows. Like that.
Okay.
Then next is, I guess I expect the answer from Sri Naresh. Which of the following filter can be used to extract the? It's like if it's wrong, it's also fine. The basic waveform corresponding to the vocal tract response from a voice pitched signal. So we only saw one of the filter. Even if you don't know which particular filter follows, there was only a single filter today in the slides. So that's the only answer here. Okay, go on. Yuvraj, you want to try? Yes.
Homomorphic filtering, man.
Yeah, yeah. I don't know where those two are. Okay, let it go. So, in homomorphic filtering, to separate a convoluted signal, the logarithm is applied in which domain?
Is it both A and B?
So, if it's convoluted signal, so in which
Convolute.
what just think about it for a while.
To separate the logarithmic transform is applied in. Oh, wait a minute. Um, Frequency domain.
Mostly. Yeah, yes. Then, which of the following does not belong to the signal acquisition of the SCAD based on the biomedical signal? I also said that at first. It's a transducer, artifact removal, analog to digital conversion, or amplifiers and filters.
Signal acquisition. Uh, can you give me a hint that it is the first or second part? I am just confused. There are three parts in the biomedical signal, that block diagram.
Yeah. So, hmm. So the first
So,
part was the signal acquisition. Next part was the signal processing. Later part was the extraction of the features.
okay. Option B, artifact removal.
Well, yeah, yes. Yes, you'll be answering. Okay, which of the following statement is true for a 1 minute recording of screening ECG? Do we use an abnormal beat as a template, or do abnormal beats produce a high correlation coefficient? Correlation is higher for them, or normal produce higher one? Okay.
I
Yeah,
have
yes.
seen in your slide only that the option C is, I think, is correct. It
Option
is
C
written in your slide only, I think.
in my slide.
Yes. Higher, or maybe I am wrong. See, normal.
So what we saw now, that correlation coefficient was higher for abnormal waves or for normal waves, where we used a normal one as a template.
Hmm. Correlation coefficient.
So assume that we have the normal template as the reference baseline. So first option is eliminated. Second is also eliminated because we don't use an abnormal template. Abnormal beats also don't have a high correlation coefficient. It might have if the QRS complexes are being matched. But then if we say that normally for 1 minute or any recording of ECG, we always take the normal beat of an ECG as a template. So when we are convolving something with its own type, the correlation is higher, but not with its it's like complementary part, the correlation will be lesser. So essentially, the option that normal beats produce a higher correlation coefficient when they are matched with each other. Basically, an autocorrelation. So answer was D. So, which of the following statements are true or is true? Ischemia means lack of blood supply. Ectopic heartbeat is irregularity of the heart involving some skip beats, or it's an irregularity of the heart involving some extra heartbeats.
Is it B?
B or D?
I think B, man.
Is an irregularity of the heart involving skipped beats. Or some, I guess it should be D.
Oh,
Just because ischemia is lack of blood supply. Then this is missed, also having some more. So both of them. Okay.
I remember your example of hiccups, so it left me out.
Oh, okay, okay. Okay, so which of the following statements is true? Bundle branch block causes the smaller one, causes longer, or has no effect on the QRS complex. Essentially, it has an effect, but what's the effect? If it's a longer or if it's a smaller?
If I am not wrong, uh, we have seen in the slide that bundle branch block causes a little of a spike in the P and Q wave, I think so. QRS in some
Q,
complex.
Q complex, huh?
So is it smaller or longer? So it has effect, right? But I think it's smaller.
So here, smaller means that smaller in amplitude. Longer means longer in time. Essentially, it spreads out like that.
I think smaller Q causes a
Okay.
smaller QRS complex.
I guess
Effect,
B.
it has effect.
It has effect, but what we saw is like the signal spreads out. So we also saw that okay, the energy is being spreaded over the entire duration. So you can't actually differentiate in between P, Q, R, S. But there are different kinds of wave to it. So the spike is highest. But for the spike to be highest with respect to the normal beat, it is being spreaded out. So it's not essentially that smaller, but it's spread it. So that's why it's longer.
Okay.
So it takes more time.
Okay.
Okay.
I think
So
it refers to the disturbance.
yeah, yes. So when basically what happens is that one of the ventricles get the supply first, another is not getting it. So they're staying sometimes to depolarize. So that particular time is being widened out that way. So this we didn't saw, but yeah, I forgot it. So there was one property associated. Okay, let it be. The answer here is minimum phase signal. So there's a property of this minimum phase signal is that if you take a signal and you convolve it with some other signal, essentially the output is always delta function or impulse. So when you take a Fourier transform of it, it's essentially the signal and it's inverse sided. So it's always one sided, and the signal you'll get with this inverse of the other signal. So if a signal and its inverse is one sided with a finite energy, say if it's causal, then the signal is a minimum phase signal. I forgot to introduce this point, but yes, this was important. Okay. Then here, this I guess we saw, huh? Which of the following statement is not true for a complex epsilon? Is that it's of an infinite duration, or of a minimum phase signal is causal, or of a maximum phase signal is anti-causal, or of a real signal is imaginary? Okay. We
Is
saw
it
that
MSQ?
what?
Is it MSQ?
Probably it might be. I don't remember. Some had single option, some had two
Partial,
or three.
partial is not compressed real signal. Option D.
Complex of a real is imaginary. Okay. Yeah. How did you say so? Because I thought if it's real, then it's real. Then
Yes.
if it's
Not true, not true. It's not true. So in the slide only it is written complex
Hmm.
spectrum of a real signal is real.
Hmm.
But if you see in the internet, I have also found out that if we take the complex spectrum of the real signal, it can be both real and
Both.
imaginary both. So I don't know.
Hmm.
I get confused here also.
No, yeah, actually that's a point. Hence, I was also confused. So, if you actually take a signal and separate the frequency components out of them, you always have the phase that's playing a role, and phase is always associated with the imaginary part. So, if imaginary part is being there, so we might need to see it again that okay, how it's not true for a complex spectrum if it's actually if it's like oh, if it's a real signal, then it should be real. It should be both, I guess. Should depend on the signal mostly.
Should depend on the signal. That is also written.
Mm, okay. Okay, then of a composite signal is the product of the substrum of minimum and maximum phase signal, or the ratio, or the addition, or the subtraction.
We can कंपोजिट सिग्नल को दोनों ही प्रोडक्ट के फॉर्म में लिखा जा सकता है तो सबस्ट्रम अगर लेंगे इज इट सी
Because we saw that it was addition of a transfer function and the excitation function. So C. Yes.
yes
So I
in the
yeah, go on.
yes in the like I think you don't include in that in this slide but in the lectures it is written there that composite signal can be represented as the product of both minimum phase and the maximum phase. So if we take the substrum, then it will be the addition of the substrum of minimum and maximum phase signal according to the log property and all
Log
things.
essentially. True, true. Yes. So that's it for today. Thank you. If you have any doubts, you can stay back and let me know.
Ma'am, I
Yeah.
have a doubt that can you please open the logarithmic one question that you have included frequency domain, time domain, if you know assignment are only. Like there is an option of frequency domain, time domain, both B, A and B, like this.
This one or this year's?
No, no, no. In this one only, I have doubt.
Okay, wait.
Assignment are.
Yeah, yeah, yeah.
Just do back, I will tell you. Ah, yes. Uh,
This one?
no, no, ma'am. Forward, forward, forward. Wait a minute, ma'am.
Yes.
That one only.
Ah.
If we from the logarithmic transform, if we take the exponential transform, then what is the answer of this thing?
If we don't take an logarithmic transform and we directly take an exponential transform.
No, ma'am.
So,
मीन्स अगर लॉगरिथमिक ट्रांसफॉर्म की जगह एक्सपोनेंशियल ट्रांसफॉर्म होता like there is
ah,
a block now in the homomorphic filtering that it is included in the last that it is in the last that exponential transform we take
huh,
for make the signal or in its original state. So
yeah.
will we take the that convoluted signal, is it important to be in time domain or frequency domain? Actually I want to ask that doubt this time at that point of time when I am asking.
I didn't get. It's like you say it again. I actually didn't get what you're trying to say.
Okay, 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 I will fully repeat the question. Like in homomorphic filtering, to separate a convoluted signal, the
Hmm.
exponential transform is applied in, like there is a exponential transform block we have
Last,
seen
at
at
last,
the at last.
at last. Yes. Hmm.
So it can be in time domain or frequency domain or both. I want to
Yes.
ask that.
Yes, it can be. So it depends if your original signal was in time domain or frequency domain. So essentially what you want is to retrieve your original signal back. So if you started from frequency domain, there's no need to convert your signal back to time domain. But if you started from time domain, if you're doing the processing in frequency domain, you need to convert it back to time domain in order to retrieve the original signal back. That's it.
Oh. Okay, so that means it can be both in time
Yeah,
domain
can
and
be.
frequency.
Yes. So here it's not essentially mentioned that okay, for this convoluted signal is in time domain or frequency domain. But yeah, if I mention, if we are just looking at the slides and then I see the question, then it would be just very obvious to me that okay, it's a real signal, and in frequency domain they are multiplied, and then if I take a log of it, they are added. So then I can apply linear transformations on it and perform the later processing. So then the option would be in time domain or in frequency domain. So there it would be like that.
Okay, okay, ma'am. Just one more doubt.
Yes.
Mm, just a minute.
Yeah, 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 yeah. Take your time.
Okay, ma'am, done. It's like previously I have doubt, but now it's clear.
Okay, that's it then. Thank you.
Okay, thank you, ma'am.
Okay, Yuvraj and Jiva Purnima, do you have any doubts? If not, you can leave. It's like the session is done. If you have any doubts, you can stay back and ask me. Do you have any doubts? I suppose you're there in front of your devices. You can speak it up. I'm also a student like you, so don't feel shy in front of me. It's fine. Have anything? Okay, one left. Yuvraj? Okay, I'll probably stay in the session till 8. Let me know if you have any doubts. Okay, I guess you aren't there, so perhaps I'll complete the session here today. Thank you for joining, and I forgot something. So, okay, it's fine. So, thanks for joining for this session, and I hope you all had fun and happy learning. Thank you.